our objective for today is but maybe okay, but if we zoom in so much, maybe I will need to change the way I run the code, because I wanted to run the code in VS Code, but given that we zoom it in so much, actually I will present it in another way. So I will present you the code. Let's try doing it the way I planned, and if it doesn't work well, we will think what to do. Okay, so anyway, so the first part of the workshop is how to read in your data. And the data I got was the data that hopefully is similar to the kind of work that you are doing. So first, let me open the data description file. And we have data recorded by some IoT device from several points in the house. And here the data description file contains the meaning of different columns of this data. The data is available from the organizers if someone is interested in it. But what is important is that we have essentially 3 files in it. So let me start maybe with the bottom. So first is the data recording from Veranda, where in first 2 rows we have some metadata of the file. In the third row we have column names, and in the following columns we have the data. So for example, we can see that this row contains some numerical timestamp. Then in blue here we have information about the time the observation was recorded with the precision up to seconds. Then we have information about the temperature measured and the humidity measured. And also note that we have one more column which is in this file missing because we have a comma, and after comma there is nothing, which means that we have an empty column in this file. And this is a typical situation in data processing, that you have something that is called CSV file, but it's not fully CSV because it has some initial data in this case, and some in this case some extra column that is not present. If we switch to Loft, the Loft file is very similar. It has the same columns, except that we now have this last column, and we actually see that this is a CO2 level measured, but the remaining data measured in the Loft are the same. And finally, we have, maybe before moving forward, let us have a look that this data is recorded in intervals of around 5 minutes. So we can see that not exactly, but from this to this moment is around 5 minutes, from this to this moment is around 5 minutes, etc. Similarly, for Veranda, we have approximately 5-minute intervals between measurements. And the last file is Attic. So this file is much wider. It has many more fields of data, and also it has a bit different way of structuring the information. So first of all, we can see that we have a separate column for day, month, year, hour, minute, and second, and then many more different measurements. And what is important here, it's important to see that this device measures, gets a measurement exactly every 10 minutes. So in the previous 2 files, we had time measured with precision to seconds, and it was around 5 minutes interval, not exactly, as you can see, there are different seconds. And in the Attic file, we have exactly 10 minutes interval. And so that's why there are 0 seconds everywhere. So what will be the objective of our analysis is to align the data contained in those three files. So with data about loft, data about veranda, and data about attic, to align them so that we can have matching information about loft, veranda, and attic. So because in loft and veranda we have only temperature and humidity, I concentrated on temperatures, or also from attic we have many measurements, but I just picked as an example for today one measurement of temperature, so that as a final objective of our data analysis process, we will want to check whether temperature in loft, veranda, and attic, do they align or not. So those are the input files. So now let's check how we can analyze them. So first, I load several packages, and let me comment briefly what those packages are used for. So the chain package is used for linking several data analysis steps together. CSV package is used for loading the data. DataFrames is the package used for working with tabular data. Dates is a package for working with dates in Julia. Interpolations is used for interpolating data, and we will need it because, as you saw, those all files have a bit different spacing of data. So in order to get a proper alignment, of course, you can do it in several ways. I will use interpolation. And finally, plots is a package for plotting the data. So first, let's read in the data. So the simplest file to read in is attic, because as we can see, it didn't have any header, etc. So we can just read it in. And now I read it in. This is the process of reading the data. So I say for the CSV package to read this file into a data frame. And here we see this data read in, but because I needed to zoom in, we do not see much. That's why a very nice feature of Julia is that in Visual Studio Code, I can click here on the left-hand side on this Julia icon, and then I can go to the attic object. And if I click on a table icon here, I have a nicely opened table viewer for this. So I can see all the columns in my data frame. As we can see, there are a lot of columns here and a lot of rows. Actually, we can see that we have over 4,000 measurements, and we have 45 columns in this data frame. In a similar way, we can read in the loft and veranda data. The only difference is that I'm showing header equals 3, meaning that the header of the file is in the third line. Why? Because as we saw earlier, first two lines are metadata that we are not interested in. That's why I'm using the header equals 3 option. And first, I'm reading the loft data, and in the same way, I'm reading in the veranda data. So here, let us see one important thing, that we have, for example, this column with time, and this column is read in a string. It's indicated here that we see that the column type is string, meaning that this part of information is collected as a string. So it's not yet recognized as a date, because we didn't specify any format to parse it. We will need to parse it somehow, and I will show you in a second how to do it. But before moving to this, we remember that the attic data frame had a lot of columns. So it is useful to maybe use a function called describe that shows me the contents of the columns in my data frame. So again, because we needed to zoom in, it now doesn't nicely fit into my screen. So I will try to resize it. So now we can see that with describe attic, I get a description of every column of the data frame. So each row in the output is 1 column. So for example, for day, I can see that days are from 1 to 30. Months are only 9, so the data is only from September, 1 single year, hours from 0 to 23, and minutes from 0 to 50. So, and then we have more and more of different columns. We will want to concentrate on one column. The column we will want to concentrate on is attic living win temperature, which is one of the temperatures measured in relation to the attic. I could have picked another one, but just I wanted to use one to keep the example simple. So now let's have a look maybe again at describe what I want to keep in this attic. So we want to keep the date information and we want to keep this attic live within temperature. So I specify that I select from the attic data frame columns between day and second, as you can see here. So I say I pick all columns between day and second. So this will be day, month, year, hour, minute, second. This is what I collect from the data frame. And then I collect a column called attic live within temperature. And this is column number 40 here. And as you can see, even though this column has a minus in its name, it's not a problem because I pass the column name just as a string, which means that I will be able to nicely work with it. So let's try now selecting from the original attic data frame only the columns that are interesting for me. And now I will maybe make it a bit wider so that it's visible. Yes, so we can see, okay, so I can know how much. Okay, so now we picked only the columns that are interesting for us. So day, month, year, hour, minute, second, and this temperature, one of the temperatures measured in attic. For the loft, maybe let's have a look at the loft data frame again in the viewer. For the loft, we have timestamp, time zone, temperature, humidity, and CO2. And as an example, I show you that I want to pick the column number 2 and number 3. So above, I used column names for selection, but equally well, I can use column numbers for selection. So if I create data frame loft 2, I say, okay, from data frame loft, just pick columns number 2 and number 3. And now I have the columns time zone and temperature picked from the loft data frame. And the similar process I do for veranda. So now for veranda, I also pick column 2 and 3. So now what we have 3 data frames, attic 2, loft 2, and veranda 2, which have the same structure or almost the same structure because they have date information and some temperature information. But the issue is that the attic data frame, as we remember, has the date separated into day, month, year, etc. And here we have a date that is kept as a single column as a string. So because of this, we will want to process the data stored in loft 2 and veranda 2 data frames so that I split this string into year, month, day, hour, minute, second. So how do we do this? I create a helper function in Julia. So here, let me define it, and I will explain you how it works. So first of all, what it does, it takes a date as an input. And I say that this date must be a string. And this is very useful feature of Julia, that I can restrict the type of input that my data frame accepts, which is useful, for example, for debugging. So if I by accident passed an integer to this function, it would error. So let's have a look as a single string, I would want to process. So such single string has the following form. It's year, month, day, separated by slash, and then space and hour, minute, second, separated by a colon. So how do I split it? Well, there is a nice split function that can take a regular expression as a splitting rule. And my regular expression, we don't have time to discuss regular expressions in general, but what it says that I split on either slash, space, or colon. And if I do this, I can see that as an output, I get a vector nicely split into year, month, day, etc. The only problem is that those are strings. So that's why the next step I need to do here is to parse those strings as integers. And and if I do this parsing, let me show this parsing manually. Now I get a vector of integers, and this is what we want. The thing you might be surprised, why do we need this dot here? We needed this dot here because with dot I say that parse every element of the input vector into the output vector. So dot shows me that I want to process, to vectorize the parsing. And finally, what I return, I want to return a nicely structured data. So I want to return a data structure called named tuple in Julia, where first will be day, then month, then year, hour, minute, second. And you must ask, why do I choose the order day, month, year, hour, minute, second? Well, it is only because this is the order of columns in the attic 2 data frames, so that I have the same alignment of data. So if I now use the process date on our veranda 11 input, I get a nice output: day 1, month 9, year 2023, hour 0, minute 4, second 47. Okay, and now what I want to do, I want to transform, for example, the loft2 data frame in a way that I split this column into day, month, year, hour, minute, second. Now, you saw that earlier we used a select function, which created a new data frame. If I append a bank character to the name of the function, it will mean that I will not create a new data frame, but rather I will change the data frame that I passed to it. So this means that with bank operator, I'm not creating a new data frame, but I will transform the loft2 data frame in place. And how do I transform it? So first is, I want to transform the first column by the process date function. And I add here information by row. By row means that this function should be applied to each row of the data. And the reason is that I simply want to split dates in every row separately. And this as table here indicates me that I have actually multiple columns in the output. So I want to create multiple columns in the output. And the number 2 is simply that I say, and keep the second column as it is. So if I run this operation on loft2 data frame, now we can see that this loft2 data frame doesn't have anymore the string as an indicator of date, but I have a nice day, month, year, hour, minute, second, and temperature column. And I do the same process for veranda. And I have nicely split the string indicating the timestamp into day, month, year, hour, minute, second. Now, after I did this, the question is, okay, but how do I align those three data frames? And the simplest way to do it is to join them. So I will use outer join, meaning we are joining two data frames, keeping all the rows in them. On what I want to join? Well, on the specification of date. So year, month, day, hour, minute, second. And one more thing is how do I want the columns of the produced table to be named? So I have this special rename calls option, and because in the front, so in attic2, I'm passing an empty string. This means that I will not rename columns in the from this data frame, but for the loft2 data frame, which has a column temperature, I will want to append temperature loft to it. So now let's run it, and maybe I will try to make it wider. And we can see that I have first the columns on which I joined the data. Then I have this active living wind temperature from the attic, which is not renamed. And for the loft temperature, I have this loft suffix. And what is the default order of rows? So here are the first rows, are the rows for which the dates matched. And we see that there are very few of them. Then we have rows that were only present in the attic data frame. And finally, we finish with only rows that are present only in the loft data frame. So we can see that actually we have very few matching rows, matching exactly. And in a similar way, I can append the veranda 2 to our result. So now in a single data frame, I have, again, time, then attic temperature, loft temperature, and veranda temperature. And now we can see that we have even fewer because we only actually have only two timestamps for which we have data collected for all from all three places. But this is because, as we have seen, each of those measurements is did in a bit different intervals. So to fix this, first thing we need to do is probably to sort the data frame. So now I'm sorting the data frame on time. And again, maybe let me make it wider. And now we can see that actually the data is interweaving. So the first row is from the attic. Then we have several measurements from loft and veranda, not aligned. Then we have attic again. So what is the thing that we will want to do? Well, we will probably want to somehow fill in the missing data with interpolation. So for example, I have this temperature and this temperature. So we will want to interpolate what is in between with the data, with linear interpolation of those two values. And similarly, for example, between this one and this one, we will linearly interpolate those values. But what we will start with, one step that will be useful for this process is to create a new column in our data frame. So from columns year, month, day, hour, minute, second, I want to create a date time object that is a Julia object for keeping time information. So again, I have created this timestamp object, and now it is indeed a single column that is a timestamp that we can work with. Let us maybe check that indeed our data frame is sorted by timestamp, and indeed it is. And now the first part of analysis is to check how would our data look, if we just plotted on a single plot the timestamp that we have just created versus attic temperature, loft temperature, and veranda temperature. And because we have missing data in the input, in order to get a nice plot, I need to drop missing values from it, but I cannot drop everything. But for each subplot, I need to only drop the data from the respective column that is missing. So if I want to plot attic, I need to drop missing only from attic. And here, this chain, we don't have time to exactly describe it, but this chain operation allows me to chain several operations on a res data frame together. So first I drop missing in it, and then I plot it. So this operation here will produce me a plot. And as you can see, the first operation is plot. So I'm creating a new plot, and the following operations are plot bank, which means I will add an additional layer to the existing plot. And here is the result. So let me properly zoom it. So we can see that now we have information about attic, loft, and veranda, and the plots look nice because on plot, of course, we have interpolated data. We seem to have a similar kind of seasonality in the data, but actually, if I wanted to plot, for example, attic against loft, we remember that we had very few time moments on which the data matched. That's why we will need to fill in the gaps. And to fill in the gaps, the first thing we do, I will change the timestamp into a floating point number. So this is a so-called a Unix Unix time measure. This is a floating point number. It is number of seconds passed from 1970. And this will be a nice number, which allows me to fill in the gaps. So again, we don't have too much time. So again, I'm just showing you that what we do. We are using a linear interpolation function from the interpolations package. And I will create a new vector that is x field, so with missing values field. And here I show you that it's fully okay in Julia to use for loops, and they will be fast. The only thing you might be interested in, so why not? I am not filling all the missing values in my data frame, and the reason is that if I look at this data frame, for example, we can see that for loft and veranda, I cannot fill the first row because I have no values to interpolate. I have to start interpolating from the second row. And similarly for attic, I cannot interpolate into final rows because I don't have a value at the end to interpolate with. That's why in the code, I get this non-missing information, and I get a range from minimum non-missing row to maximum non-missing row, so that I'm not trying to extrapolate, I'm only doing interpolation. So I'm creating this function to fill in the gaps. And now I am transforming my data frame. Again, this bank here, which means that I will not create a new data frame, but I will add information to an existing data frame and create a new three new columns, T attic, T loft, and T veranda, which will have gaps filled. And now, before maybe plotting, let's make sure that indeed this data frame has the gaps filled. And if I go here to the left, to the right, we can see that indeed, although attic column had missing values, like here, those missing values are filled in the T attic column. And now, as I have filled in the missing values, actually, what I can do now, I can plot, for example, temperature with attic versus temperature in loft against each other. And now I will get a nice plot showing one against the other. Again, here, what I did, I created 3 plots on a one image, and we can see that indeed the temperatures in loft and attic, loft and veranda, veranda and attic are correlated. And of course, I could do some more complex analysis how they are related, but at least now I have a working information that I can move forward with some more advanced analysis. So to sum up, what we have shown is that we had 3 files that have a bit different data structure, that had input data that needed cleaning, and this was the first part, that I made this year, month, day, hour, minute, second in line. And second, I joined those data frames. And after joining them, I noticed that they have misaligned timestamps. And because they had those misaligned timestamps, I used imputation. Of course, you could use some other technique, but I decided to use imputation as an example to have data that for each timestamp here has all the data for all our temperature in attic, loft, and veranda, which allows me later to use the analytic tools that you will discuss in later parts of the workshop that allow you to analyze this data. So in summary, DataFrames package has all those nice features to prepare the data. So you get some maybe not bad data, but not super clean data, the data in different formats. And all about data frames is how to prepare the data for your further analysis. So, of course, there are a lot of details how to work with data frames. So if you want to learn more, there is a manual page of DataFrames.jl package, where, first of all, the manual itself has a lot of examples, and also here in the initial section, you have a lot of links to a lot of tutorials and manuals that will show you how you can work with the DataFrames package. So I hope those examples were useful to give you an intuition how you could work with data frames. Of course, if you are interested in this file, then please contact me without hesitation, and I will gladly share it with you. And the source files that I used, so those attic, loft, and veranda files, are provided by the organizers. So that's why I hope that you can also get an easy access to them. They were selected specifically because we assumed that this type of data is the typical data that you would work with. So you might want to see how you could work with it using Julia. Okay, so thank you very much. Maybe now I will stop sharing, but we have a few minutes left. So if someone has questions or would want some clarification, then please do not hesitate to ask.
Yes, please.
Is there if you're a Python programmer and used to Python and you switch to Julia, so what is there like a different philosophy between Pandas data frames and Julia data frames, or are they do they basically do the same thing and work in the same way? Although the semantics is a little bit different, of course, to different programming languages.
I can repeat it if you did. Yeah. So the question.
Understood.
So the question is, if someone switches from, or maybe you heard it.
Yeah, I heard it. So
yeah.
So there are two major conceptual differences. So first is that DataFrames package is concentrated only on mechanisms and algorithms that are used to transform and work with tabular data. So for example, this means that things like select, as we have shown, or for example, joins, like here we have the outer join function. Those are the functions provided by this package. But as opposed to Python pandas, DataFrames package is not monolithic, which means that if you, for example, need interpolation, you need to use separate package interpolations. If you want plotting, you need to load separate package for plots. If you need dates, you need to load a dates package. If you need reading CSV files, you need CSV package. And for example, here, if you want the functionality allowing you to nicely chain several operations on the data frame together, you need, again, a separate package. So this is the first difference in philosophy that new users often find maybe challenging, that it's not enough to just load a data frames package and you have everything. The reason is that in general, the design of the Julia language is that it's super easy to integrate different packages together. And for example, I used plots for plotting, but there are other plotting ecosystems in Julia. All of them are very nice. And DataFrames doesn't force you to use one type of plotting. You can use whatever types of plotting, but this means that you need to know which one you want to choose. So this is the first difference. In short, DataFrames has only functions that are designed for working with DataFrames themselves. But for example, if you want to have interpolation of your data, you won't have such a function in DataFrames. You need to use another package. And this is different from pandas, which pandas has a philosophy like batteries included, which means that if you load pandas, you have lots of helper functions that are often needed in data analysis. So you just you can just load pandas package, and for example, plotting is already inbuilt into pandas. Of course, you can use other plotting if you want, but you have inbuilt plotting in pandas. So this is the first big difference. And the second difference is that in general, what you can see here, like for example, this process date function, or here I defined a fill gaps function. And even here within this fill gaps, you have a for loop. And this is the second big difference conceptually, that this is a normal design pattern in data frames and in general in Julia, which means you don't need to look for a predefined function that does the exact thing you want because of performance. Why? Because Julia, if you have a user-defined function like a fill gaps function here, it will be very fast, even if it's user-defined, which means that it is a normal practice to create your own functions and then just pass them as operations that you perform on a data frame. So again, this means that very often users ask, do we have some specific function in data frames or in general in ecosystem for doing a specific thing? And of course, if the thing is super common, then probably there is some package that defines it. But it is a very common practice that you create your custom made functions, like for example, this process data or whatever. Why? Because you don't have to rely on libraries created by someone else and written in C or C++ to have a fast execution time. If you create your own function, it will work very fast by itself, which means that, again, conceptually, it's very often that you write your own functions and just call them from the data frames package or some other packages. So I think those are the two most important differences. In the past, the third difference that we would discuss would be that if you have data frame, it has inbuilt handling of missings. And this is indicated even in the type of column, because this question mark here indicates that in this column, missings are allowed. And in Pandas, this support of missing was not so obvious, but with the release of Pandas 2.0 and going into the direction of arrow types in Pandas, also in Pandas it's get now pretty similar. But it's also worth to note that DataFrames from the start has a full support of proper handling of missing values in any column of any type. So those are probably 3 things to remember. Thank you.
Thank you. Just one comment. You have written a book about DataFrames, I think. So for those that like to read books, maybe it's listed in your homepage.
Yes, so it's listed here. So actually, the documentation has a link to 2 books. First is Julia for Data Science, and second is Julia for Data Analysis. So Julia for Data Science it's not mine book. It's it's a very nice book that is freely available, online. Just you can click through it, etc. I have written a book, Julia for Data Analysis, and it has also a website where all the code is available for free. But if you like a printed book, then you can buy this book on Manning, and this is like a normal book as any other book provided by Manning. And all the links here are in the DataFrames documentation.
Very good. 2 more questions. I think when you have imported the data and treated them the way you want, suppose you want to save them, would you save them as CSV files or some other file format?
Yeah, so it depends. There are multiple file formats supported. And I think that it's best to go to the section of the manual importing and exporting data, and CSV files is one of the options. It is pretty popular because very often people interoperate, for example, between Python, R, Julia, or whatever, using CSV files. But there is a host of other formats supported, and you have links here to the packages. So, for example, Apache Arrow is pretty popular. Apache Feather, Apache Avro, JSON, Parquet, Stata, SPSS, SAS files. We can read in R files. We can read in Excel files. So there are many options. If you ask me which format I typically use for working with data, I use Arrow. So Arrow becomes pretty much a standard, as I have just said in a second. If you use Pandas also is now switching to the Arrow standard. So this Arrow standard also, for example, Polars in Python also uses Arrow. So Arrow in general becomes a de facto standard for working with tabular data, I would say. So this is a pretty popular format, but of course CSV is so present in so many places that it's also a format that is fully supported in Julia.
Follow-up question here.
What if you work with really, really huge data frames, like millions and millions and millions of points, and you want to store it on file and then just retrieve it really fast, like HDF5, for example? What would be the fastest file format to use for really big data frames?
So it depends. What do you mean by really big? But there is an HDF5.jl package that is used for reading HDF5 files, but here one comment is because you are asking specifically about HDF5, so I'm sure you know that this format is much more complex. So it's not just for tabular data. it's for arrays, for multiple nested data. So it's a much more complex format. And HDF5.jl package supports all its complexities. So we are not limited only to tabular data. If you have three-dimensional arrays or whatever, you can also process it with HDF5.
But if you just want huge data frames and fast storage and retrieval.
So I would say that again, arrow format is now a de facto standard for huge data frames, especially that if you have a really huge arrow file, this arrow file actually doesn't even get read into the data frame. So here is my blog where I weekly write a different information about working with data in Julia. So it's every week, so over 100 posts. And one of them is how Arrow works. And what I show here is that you have a really huge Arrow file, which is read in, maybe not like super big, but at least, it's 10 million rows, and it's read in, as you can see here, in a fractions of a second. And the reason is that if you have an Arrow file, so this memory layout format is designed in a way that you can read it into a data frame, but without reading it from a disk fully. So actually, if I have a data frame created from an Arrow file, this table, it does not even reside in RAM. It's only stored on disk, and it's only read in chunks as needed. The limitation is, as you can see here, that you cannot modify it. So if you have data stored only on disk, then it's read-only. But with this small limitation, the benefit is that you have a super fast reading of super huge data, because this reading doesn't happen eagerly. It happens lazily. Only the part of the file that is needed is read.
Good. Final quick question. If you make a loop where you loop through the elements in the data frame, how fast is that compared to looping through arrays?
No, so like here, yes. So so the details are a bit more complicated to what I will say now, but in general, you can assume that they are as fast. So they are super fast. But if you want more details, of course, they are there. So there is something that is called the DataFrames tutorial using Jupyter notebooks. And there is one of the notebooks is about performance. And here it collects the most important guidelines, what are potential pitfalls, performance pitfalls. But they are a few and they are easy, but in general, the general conclusion is that if you remember about one or two rules that we don't have now to discuss, it's just as fast as arrays, because essentially, if you have, for example, day column, this is a simple vector in Julia. So this is not any special data structure. It's just a normal Julia vector.